The premier award of the profession, the gold medal, is awarded only when there is an outstanding candidate. It is given to a professional engineer who is recognized widely as a distinguished practitioner of the profession and has rendered outstanding public service in other fields on a federal or provincial basis. The recipient should be recognized by the public as a professional engineer and a dedicated public servant who has made significant sacrifices of time and effort to benefit society. The recipient of this year's gold medal is Dr. John McPhee.
My name is John McPhee. I'm a professor at the University of Waterloo in Ontario, Canada. I finished a PhD in 1990, and after that I spent a year at an aerospace lab in Belgium and then a vehicle dynamics lab at Queen's University in Ontario. I then came to the University of Waterloo, where I've spent the past 30 years, including sabbaticals at MSC Software in Ann Arbor, the Canadian Space Agency, and the Toyota Technical Center. And over that 30 years, I've spent my time working on fundamental modeling of dynamic systems, and then specifically on applications to an electric and hybrid electric and autonomous cars. More recently, looking at systems in which a human is interacting with a machine, what we call biomechatronic systems, with applications ranging from exoskeletons to rehab robots to even sports equipment. At Waterloo, I spent my first 10 years focusing on really fundamental questions in dynamics, systems modeling, and controls. For the next 10 years, I focused on automotive systems. I was a Toyota MapleSoft research chair, and I developed next-generation electric and autonomous cars. Now, for my last 10 years, I've been studying a much harder problem, and that's problems in which the human is involved, because humans are incredibly difficult to model and predict. So the study of biomechatronic system is the study of humans that are interacting with their tools or their machines. What we try to do is we try to develop unified models that include both the humans and the machines, so that we can either improve the performance of the human, whether it's an athlete or a patient, or we can improve the design of the machine that is helping the human achieve some task. So applications in the field of biomechatronics include our stroke rehabilitation robot, where we have models of both the patient and the robot in order to come up with a system that tunes the rehabilitation process for an individual patient. We also have models of humans using exoskeletons, whether it's for the upper arm or your lower limbs, and by combining these models of the human and the exoskeleton, we've come up with better controllers that minimize muscle fatigue and effort and maximize the performance of the human. Biomechatronic systems also include sports. So for example, a rider on a bicycle is a human interacting with a machine. So we've developed some very detailed models for our Canadian Olympic cycling team that allowed us to optimize the design of the bicycle for an individual athlete and then show the athlete how they can improve their performance through slightly different pedaling strategies. We also do a lot of work in the golf space. We've worked very closely with the Canadian wheelchair basketball team on a couple of different projects. In one project, we used a unified model of the human and the wheelchair in order to determine optimal push strategies. In the hockey space, we have a patented hockey skate blade design, and we also developed the very first hockey slapshot robot. So another sports project that we worked on was a baseball pitching robot. This was a project that was led by two of my students, who then went on to patent their design and commercialize it. And in fact, this robot is now adopted by every Major League Baseball team. The robot can reproduce any pitch that's been thrown in Major League Baseball in the last 5-10 years. It consists of a 3 gimbaled roller system that will create exactly the right speed and 3 components of spin, including gyro spin. Another project we're working on right now is optimizing the placement of hip and knee implants in replacement surgeries. There are tools available now to tell the surgeon where they are placing these implants, but there are no tools that tell the surgeon where they should be placing these implants for a specific patient. And so we've been able to create detailed models of patients that combine X-ray images with physics-based models so that we can optimize the placement of these implants for a different patient. Well, when I heard I'd won the gold medal award, I was thrilled, ecstatic. This is a tremendous honor, literally the greatest honor of my career.
Dr. John McPhee has become Canada's leading expert in system dynamics, and the impact of his work is being felt in many sectors. He has also contributed enormously to engineering education at the University of Waterloo, making him a very worthy recipient of this year's gold medal.